Okay, this is where we stopped last time, so let me just go on here and then I will give you more intuition in a couple slides because we almost did this proof last time. So what were we proving? So we're proving that if you have a regular language, then there is an NFA that accepts it. We proved the converse. We proved that if you have a DFA, this is what we did basically, the language that it accepts, it's regular. We did this by actually showing that this, if you remember, RIJKs were regular and their union and so on. But now we go the other way around. Remember that we constructed the NFA, we proved that the NFAs and DFAs are basically the same thing, and we also added epsilon moves to the NFA, and we also talked about this proof, to be honest. So I'm just going to formalize it. So during the last hour, in the end, we said that in order to prove this, what you really have to prove is just a couple things. First, you have to prove that the language that consists of a single letter or language that is empty is actually accepted by an NFA. And we did construct this last time. So we did this. So on the bottom there, you see that, maybe I can use the pointer. So on the bottom, you can see so here it is. So here you can see that if you have a single letter, you accept it by just going to an accepting state like this, and everything else comes here. Everything that is not your letter also goes here, and then you get stuck here. Basically, this is an NFA, so you can do this. So you send everything to empty set, so it's like a dead state. And if you have empty word, this is what you have an accepting state, and every letter takes you here, and then you get stuck here. So only thing that will be accepted is just an empty string. If you start here. So the language that just consists of an empty string and the language that consists of just single letter like this will be accepted by NFA. This is trivial. Well, not trivial, we constructed it here. And now what we have to do, as we discussed before, is we have single letters, we have epsilon. Now I have to construct a union, concatenation, and a star, and I'm done. Because this is all regular languages are. And we did this last time as well, right at the end. We talked about this. Actually, some of you solved this. So if you have language L that is accepted by an NFA, and you have language L prime that is also accepted by NFA, you can construct a language that is exactly concatenation of these two. Well, you're constructing an NFA, M double prime, that exactly accepts the concatenation of these two and nothing else. And how you construct it is you look at the accepting states of the first machine, and you, by epsilon move, you glue it to the start state of the second machine. So if you start your string here, blah, 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 you go here, so the first machine is supposed to accept it, then by epsilon you appear in the second machine, and then you accept here, and the accepting state will be the accepting state of the second machine. This is what is written here mathematically. So you say, like, for example, the states are states of the first machine and the states of the second machine. So you have both states on this side, then you say, what is the transition function? On this half, it's the same as the first machine. On this half, it's the same as the second machine. And here you make the epsilon jumps exactly. Like if A is your epsilon, you can jump from first to the second one. So this actually proves, we did this last time, that's why I go fast. This proves that so if you have a machine for language L and machine for language L prime, you build the concatenation machine with epsilon moves. This was the whole point why we came up with epsilon moves to begin with, to actually build these things easily and not work with DFAs, which would have been much more complicated. So we have letters, we have concatenations. We also talked about the union. So if you have a machine that accepts L and machine that accepts L prime, you build a new machine that accepts the union exactly. How do you do this? You add a new start state and two epsilon moves. And now this machine, if you start here, either goes here or goes here, and there will be an accepted computations if and only if one of the machines accepted, which is exactly the union. And this is mathematically written out here. So I have a union, I have concatenation, I have single letters and epsilon. Only thing left is a star, and this is an exercise. So exercise is the fact that, let's say you have a machine that accepts language L, you have to build the machine that accepts L star. right? From the machine that accepts L, and that would mean that you will start with machines with so if you have now if I give you a regular language, how do you build me a machine that accepts it? You know that the language is regular, so you know it starts from single letters, and then it makes unions, concatenations, it makes stars, and so you just follow these instructions here and create your machine. First you create these machines here, then you do the unions and concatenations and stars according to how your regular expression describes your language. So this is basically an easy proof that shows that every regular language, there is an NFA that accepts it. So, okay, so we have to move on to an important topic called the pumping lemma, but let's just give a quick rundown of what we did so far. This was our writing last time, so let's scroll down all the way. And let's just recall what we were doing. Put this here. So what we're doing is we had the class. So let's start all the way from the beginning. So we had things called problems. This is what scientists want to solve, and so then we said that okay, problems can be identified with languages. And we had a couple examples. Let's give a couple examples again, so we have much more background now, so we can understand more things. So let's look. This is the one problem that we had. So let's make it thicker. So let's say you want to determine if a number is prime. So is n prime? Let's say this is your question. You're given a number, and you're supposed to determine whether it's a prime. How is this equivalent to a language somehow, or determining whether some strings belongs to some language? I can translate this problem into a language in a sense that I can create a language. Let's take my alphabet to be all numbers like this up to 9, so 10 letters. So this is my alphabet. So now I create language P that consists of those strings from this alphabet that contain prime numbers. That would be 2, 3, 5, 7, what else? 11, 13, and so on. So it's an infinite language, of course, and it contains all prime numbers. And if is n a prime now moves, so it translates into a question, does n belong to LP? So now let's say I prove that LP is regular, which is of course, it's spoiler alert, it's not regular. But if it were regular somehow, then I would build a DFA that accepts this alphabet exactly, right? That means that if this were regular, there exists something that starts like this, and then you have like this, and then the accepting states, whatever. So it's a DFA, and each transition takes an input, a natural number, right? So if it were regular, that means you can draw a DFA, that means you can code it in your computer as well. And how do you determine whether your string, let's say a very large one, 2, 4, 3, like something like this, is this a prime number? You just input it in your DFA. Let's take green again. So you input it here and you just follow your DFA, and if it goes to accepting state, it's prime. So somehow building a DFA algorithmically solved my problem whether something is prime if it was regular. I just proved that only regular languages constitute. So somehow the description of a language with unions and stars and concatenations was like one side of describing it, and the second side of describing it was giving you a DFA or NFA, which is the same. And giving you a DFA was basically giving you an algorithm to determine whether string is in there or not. Basically, that's what a DFA is. And it just answers the question whether I can algorithmically solve a problem. Very roughly speaking. So you can see something. By the way, you can solve all problems like this, almost all problems. So let's look at just another example for the sake of it. Let's say you want to find what is 2 plus 3. Now I will translate it into a language again. So my alphabet, I will take again just all my numbers up to 9, and I will add just 2 symbols like this. Plus, whatever, this is my alphabet. It contains 12 things. And now I will create a language, let's call it L+. Well, it's not it's a bad name, so call it L+, like this. This just contains all strings of valid additions. So 1 plus 1 is 2, 3 plus 7 is 10, and so on. So it's an infinite language that contains strings that are valid additions somehow. For example, this string is not here because this string does not represent a valid addition and equality. So think like this. And now how do I test whether what is 2 plus 3, right? So how can I assess what is 2 plus 3? What I can do is this thing is finite. We will see this procedure more in Turing machines, but let's give a snippet here. So let's say I'm looking at something like this. So what I will do is, I only have 12 letters, right? 12 things. So I number them. Let's use this here. So I number them like 1, 2, 3, ... whatever, and this will be 12, this will be 11, whatever. And I start plugging in all the possible values. So first what I'm trying to do here is, let's say 2 plus 3, and I plug in the first value, 0. And then I have the string here, and I check whether this is here or not. If my L plus were regular, that means I have a DFA. So I can run this DFA on this string, and it will reject, because this thing is not here. Okay. Then I do the second guy. So what I do is 2 plus 3. Now the second guy is 1. So I just follow this. And then I check again. Then at some point I will arrive at 2 plus 3 is 5, somewhere here. I will check and the DFA will accept. And I will say that 2 plus 3 is 5. And I can do this, so let's say I'm doing something like 17 plus 3 is 20. So first I will go all the way down here until 2 plus 3 equals. And then I will start doing things like 2 plus 3 equals 0, 1, 2 plus 3 equals 0, 2, and so on until 2 plus 3 equals 0 equals. So I'm doing all possible combinations for inputs. And at some point, well, sorry, I wasn't supposed to write 2 plus 3 here, but 17 plus 3, this is what I was supposed to do, 0, 1, 0, 2, 0, 3. I will check at 0 plus, 0 equals, and at some point I will have to check 2, 0. So I'm just following all possible combinations because this string is finite. I can do this, and I will algorithmically solve this problem, even though this is not a decision problem. Decision problem is something that has answer yes or no. 2 plus 3 equals what is not yes and no question. However, I can turn into a yes and no question by just inputting every single possibility and asking yes and no questions if I have an algorithm that is a DFA that solves it. So languages are the same thing as problems. We reiterated again. And what we did basically now throughout this lecture, so we had this huge, so we fix an alphabet A, and then we have this A star is all possible languages, and then we identified some things here. So we call this guy regular languages. These are the ones that you can build DFA for. But I draw this way, but how am I guaranteed that there is even something here? So now my question is, how do you know there exists a language that is not regular? That means, how do I know that there exists a problem for which I cannot construct a DFA? Maybe everything that I can compute is actually a DFA. Maybe this computer is just a complicated DFA. So this is the question now. And so this is what we're asking. This is where the pumping lemma will come in. This would help us to construct a language that is not regular, and that means that we have to enlarge our set of languages somehow. So this is where the pumping lemma comes in, and we go back to... So what does the pumping lemma tell us? This is what it tells us. Yeah, you can see it and enlarge it. So this is what pumping lemma says, and let's try to understand it. Let's say my language is regular. So I'm given a regular language. It says that if your language is regular, then there is a constant number n, so some 474. There always exists a number n for a given particular language, such that all words that are longer than n, so all strings that are longer than n, maybe I can draw here actually. 10. So all strings that are longer than n can be decomposed in 3 parts. You can see 3 parts. So you look at any string that is longer than n and you decompose it in 3 parts, such that the middle part is not empty. This is what the first thing says. The first half, this UV part, is shorter than n, okay? But the most important bit is here, that for any natural number you give me, uv to the power iw is also in my language. So do we understand what it says? What this says is, if you give me a regular language L, there it comes with a number n, so n is some particular number, every language comes. So it depends on your language L. So I will write this way. Then any word which is longer than this n, and I also know that it's accepted. This is the same as giving you a DFA. Always think of it this way if you prefer. So I gave you a regular language, that means I gave you a DFA. That means that if I give you a string which is longer than some number, right, and your DFA accepts it, this means that DFA accepts, it also accepts, so that means I can write your string in 3 other strings like this. I can decompose this in 3 bits, not bits, but 3 parts, such that UW, well, this is W is unfortunate, it's supposed to be X here. So UX is also accepted by my DFA, but UVVX is also accepted by my DFA, UVVVX is also accepted, and so on. So if you will produce one string that is longer than n, I can produce infinite strings this way. Who doesn't understand what pumping lemma says before we even begin to prove this? So let's see an example that why this is very useful. Let me give you an example. Remember, we had this language before we prove it. Even though the proof is very intuitive and trivial, let's look at the language like this. So this is AN, BN, N belongs to natural numbers like this. So this is just a language. Let's make it zeros and ones. So let's make it zeros and ones. So that zeros and ones. So this is just a language like this. 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, and so on. So it contains as many zeros as many there are ones. Now I'm telling you that by pumping lemma, this is not regular. Why? Let's say. So let's say this is regular. Assume L is regular. That means there exists a DFA that accepts it. By pumping lemma, there must exist a number, I don't know what this number is, such that if I take a word which is longer than this number, now this is my first question. Let's say I don't know what this number is. I just assume that this is a DFA that accepts it, and I'm saying that there exists a number. Then if I take a word bigger than this number, so my first question is, does there exist a word in this language? So W is in L. Does there exist a word in this language that's bigger than any given number? Specifically, for example, what? 0 to the power n 1 to the power n belongs to this language, right? And it's larger than the size of this guy is what? It's 2n. So it's bigger than n. So you can always find a string that's bigger than any given number. So I know that this number exists now, and I know that if this number exists, there must exist a word that is bigger than this number. So it's like this now. So I have this ... So maybe this is n, and then this is also n. So this is my word now. Now what pumping lemma tells me, I can break it in 3 parts. So breaking it in 3 parts means maybe this is part 1. I don't know whatever this is. Maybe this is part 2, and this is part 3. So I don't remember what the letters were. I think this was U, this was V, and this was, I don't know, X. So V goes. So it breaks into 3 parts. And what pumping lemma tells me, by the way, I do not know where U ends or where V begins or blah, blah, blah. I have to look at all possible. But what pumping lemma will tell me that if W is in L, and I know that W is in L, so W is in L because it's of this form, then if I double V, it also should be in L. So that, what happens if I double V here? So it will have 0, 0, zeros. So it will have U many zeros. And let's say I write 2 V's, it will look like this, right? It will be 0, 0, 0, and then 2 1s from here, and then again some zeros and 2 1s. And then I will have X here, which is just all 1s. Now this clearly is not in my language. Why? Because my language only consists of zeros and as many 1s, as many zeros. So pumping lemma told me that this has to belong to L if my L was regular, but clearly this cannot happen. So L is not regular. But I have to look at all possibilities, how maybe U is something else. Maybe V only consists of zeros. Then what will be the problem if I pump on zeros? Exactly, you will have more zeros than 1s. If V only consists of 1s, then you will have more 1s than zeros. But yeah, so it only consists of zeros, that's what you mean, right? But maybe U is large, maybe U is like this, maybe this is U. I had to look at all possibilities that can happen. I don't know which one might happen. So there are 3 possibilities. V consists entirely of zeros, V consists entirely of 1s, or V consists of zeros and 1s. In all 3 possibilities, when you multiply it, it no longer works. So this language cannot be regular. So pumping lemma tells me that this language cannot be regular. So there exists a language which is not regular. That's already interesting. That means when I had this huge language, all possible languages like this, so this was like A star, I know that regular languages are not everything. So there is something here, I already know this. All right, so where was that? It was here, I guess. No. Here. So how do I prove my pumping lemma now? So here is the exactly A and Bn is not regular. Why? And we just did why. But you have to look at all 3 possibilities and prove. Why is pumping lemma true? Now I will intuitively explain this. So pumping lemma starts with let L be a regular language. So if the language is regular, that means there is an DFA that accepts it, right? So it's like this. So there is a DFA that accepts it. I don't know. It goes on, ... Some things happen here. I don't know how big this thing is, but there is a DFA that accepts it, right? So now pumping lemma tells me that there exists a number such that blah, blah, blah. What is this number? Let n be the size of my DFA, how many states I have. I will take number. So if my DFA has 2,345 states, my n will be 2,345. I'm guaranteed that my DFA has finite number of states. This is the definition of DFA. So this n is a finite number. Now I'm asking you a question. Let's say the string is coming in, so the string is bigger than n. And I know that the string is accepted. No, let's say not. Let's say yeah, exactly. So let's say W is in L and it's longer than n. I'm claiming that when you start at your DFA and you're moving along like this with W, it has to accept, right? There's an accepting state somewhere, and your W ends here or here. So it ends at an accepting state. What I'm claiming that on its path on the graph of the DFA, one of the states has to repeat. Oh, exactly. It's bigger than n. So the size of W is bigger than n. There are only n states, so it cannot visit everything just once. It has to visit at least one of the states twice. This is called a pigeonhole argument. Why is it a pigeonhole argument? Because if you have 10 holes and 11 pigeons, one of the holes has to take 2 pigeons. Exactly, if you have n many states and your word is longer than n, then when you continue, you have to visit one of the states twice. So let's say this is the state. Let's say this is the state that is visited twice. So let me get my laser back. So let's say, yeah, let's bold it. So let's say this is the state that I visited twice. So when I started my W, like 1, 2, let's for simplicity say my W starts with 1, 1, 0, ... So I go, well, this was my start state, right? So let's say my start state is here. So I go 1, 1, 0, and then I continue, and I visit this guy again sometime. I don't know, it's a bad notation. So I visited this bold guy, and I visited this bold guy again. And so I went like, I visited the state, then I continued on some path, and I came back to the state again. So this might be a longer path like this here, and it came back. At least one of the states has to exist like this, that it came back. And your W continues here like this. Let's say 0, 0, 1. So it's like 1, 0, 0, blah, blah, blah. And it came back again to this guy. Let's call this guy Z. And then it went on again, and it accepted. Right? So W got accepted. It went on a loop like this, starting at Z and ending at Z, and it accepted. What I'm claiming is that this guy is exactly V, this guy is exactly U, and the rest that is left here is exactly X. Because if I start with the guy that goes 1, 1, 0, and instead of 1 that takes you this way, I take 0, if I cut out V at all, it still accepts. See what I mean? So if you start here, 1, 1, 0, and you do not go on the loop by reading 1, rather you go by reading 0 and you go this way, you cut out this whole V and you will still accept. So let's draw actually this guy. So in our case, W is exactly, I will draw what this is. It is 1, 1, 0, 1, 0, 1, 0, 1. Because you go, let me start my light. So you go 1, 1, 0, 1, 0, 1, 0, 1, and you accept it, right? This was your W. But I can completely skip the middle part. I can completely skip this 1, 0, 1 part. So if I completely skip this part and I go 1, 1, 0, 0, 1, I will also accept. I will not just follow this loop and that's it. Otherwise, I can go like this, 1, 1, 0, 1, 0, 1, and I can repeat this again, 1, 0, 1, 0, 1. So I repeat this twice. What this means, I went 1, 1, 0, 1, 0, 1, and then again I went on the loop. 1, 0, 1, let's erase this, and then 0, 1. You see what I mean? If there exists a state that when you start, you also end at that state, you can go as many times as you want on the loop. This is pumping on V, or you can completely skip this loop. This is removing V at all. So if you have a DFA and your number of states is Z, and you have a string that is longer than Z, one of the states is visited twice. If one of the states is visited twice, that means you can go on the loop as many times as you like, or completely skip the loop. But so the question was, if there's many loops like this, I can use any. You can use any, but you're guaranteed only that you have at least one. The guarantee comes that you only have at least one loop, like this, if you choose n equals z. So we just proved that there are languages that are not regular. And this is the same proof, like just written out, and the fact that there is a pigeonhole argument and so on. This actually finishes our, so this also goes into the recordings. By the way, we're not going to take a break, as I said, because we're just too much behind now. So we're skipping the minimization of a DFA. However, there is a 3 or 4 page PDF by Jan Peleska, which I'm going to upload to your Teams file, where you can read where this thing happens. What is the minimization of DFA? I will tell you if you're interested. So let's say you have a regular language. Of course, it's accepted by DFA, but the DFA is not unique. There may be many different DFAs that accept the same language. The minimal DFA is one of those which has the least amount of states. So minimization of DFA is you start with a DFA and how to make it as small as possible by removing the extra states that you don't need. And there's an algorithm to do it, and it's interesting, and it's written up by the guy I mentioned, this Jan Peleska. By the way, there's my website also, Nadareishvili.com, where I upload this stuff, and all the links are there, and maybe I will put that link up. But we're skipping that. It's interesting. However, we're very much behind, and there are more important things to come, which we do not want to skip. So rather skip minimization of DFA now. It might be introduced as exercises later on, if you guys will read the stuff. So now we move to Chomsky hierarchy. Chomsky hierarchy starts at the point that, okay, we have regular languages. What is beyond regular? So now we have to define other things. We know that not all problems are regular. Not all languages are regular. So there are other guys. So, okay, who is Chomsky? Chomsky is this guy. He's still alive. He was born in 1928. And Noam Chomsky, he's a linguist. He also makes nice political analysis. He's still very active, by the way, in whatever. So he's a linguist. He studied grammars. And he studied grammars, among others, he studied context-free grammars, which you're aware of, and he studied them as a purely syntactical objects. I will explain this in a minute what this is. And this was highly sensational abstraction. So this is a smart guy. So anyways, so what is Chomsky hierarchy? It's just a hierarchy of different types of languages. So the bottom of the hierarchy, the simplest one, so to speak, is regular languages. So let's how we're gonna describe languages. This is one of the important topics we are covering, by the way. So Turing machines, Chomsky hierarchy, things like this are famous topics. So how are we gonna describe now languages? For regular languages, we describe them using regular expressions like union, concatenation, and stuff. Now we are going to introduce the machinery of grammars, which you are aware of from one of other courses. You have seen it somewhere. I don't know where you saw it, but you have seen it. And so this is the way to construct languages using grammar. And we are going to, so let's give definitions and then talk later. So what is grammar? Grammar is four things. I just realized that when I turn away, I'm not recording the voice, maybe on the computer. So I'll have to face this way. Okay, what is grammar? Grammar is four things. NTPS, So what is n? N is a finite set, just a finite set. We call it alphabet of non-terminals. You have seen it somewhere in OS, yeah, or somewhere. T is finite set of terminals. So usually n will, so we will denote n by big letters. So it will look something like, so let me switch. So n will be something usually denoted like with big letters A, B, C, dot, dot, dot. Somewhere it has to end somewhere. So I chose F here, but whatever. It's a finite set. Then T will be small, we will denote them with small letters, A, B, X, maybe also 0, 1 sometimes. But it also has to end somewhere. So these are two finite sets, and I will assume that they do not have anything in common. So something cannot be terminal and non-terminal at the same time. Terminals are different things, non-terminals are different things. And then we have production rules. So most generally, production is whatever is circled here. So what this means that, so if P small is a production, if you look at this definition, this means that it's a pair. I have no erasing function here. So it's a pair of, I don't know what to call this, so alpha, beta, where alpha is n union T plus. So if you remember what plus meant, so it's a, if you take a union of non-terminals and terminals, and plus is all possible strings that consist of terminals and non-terminals, not including the empty string. So alpha can be, for example, something like A, B, C, X, something like this. So it will be a string that contains non-terminals and terminals, but it does not contain an empty string. That's what the plus bans. And beta, on the other hand, is exactly the same thing, string of terminals on term, but you're also allowed to have an empty thing. So this might be empty, but this also might be something, the same exact thing, something like this. So it's just a pair. How are we going to write this is, instead of writing this, you would write alpha arrow beta. So in our case, you might have A, B derives C, D like this. So it's a grammar that you saw before. It's supposed to give you that if you start with A, B, you can create C, D somehow. This is what production rules give you. So again, you have bunch of pairs like this, so we're not writing pairs anymore. So you have bunch of pairs like this. But again, it's a finite set. So it has to end somewhere. So it's a finite set of production rules. So basically, you're only manipulating finite sets because you want to algorithmically describe everything. You cannot have an infinite algorithm. Makes no sense whatsoever. Infinity only makes sense in the heads of human beings when they talk about mathematics. But if you want to program anything, you have to have a finite set of rules, even though your finite set of rules create infinite things. So set of productions is the rules. So you have your non-terminals, terminals, and then you have a rule how to create new things from old things, and it's a finite set of rules. And then there are some shorthands. So if you have a rule like this, U creates V1 and U also creates V2. Instead of writing it as two production rules, I write U creates V1 and I will drop V2. So this just means here that you have these two production rules like this. Just a shorthand. And then what else? So I have non-terminals, terminals, productions, and then there's just one S. S is a non-terminal I call a start symbol. And let me give you an example by this. So before explaining extended production of strings, maybe okay, I'll give you this. So let's first explain this. So now let's say, or should I give an example first? let's give you an example first, even though I haven't given you a definition of what derivation is and blah, blah, blah. But since you all have seen the grammar, I will give you an example. So let's create this grammar here. That first I have to give you what are non-terminals, right? Let's say I only have one non-terminal, which is S. I always have to have a start symbol. See, this is the requirement. So my non-terminals cannot be empty in a sense. So if you're creating a grammar, let's say I only have one non-terminal, S, and I have two terminals, let's say 0 and 1. These are my terminals. Now I will give you production rules. So let's call it P. I will write down what P is, and S will be my start symbol. So my grammar has to be like a tuple. It's not a set because it depends. It really matters where I write stuff because I have to know this is non-terminal, this is terminal. If I write it as a set, then it doesn't matter. So it has to have parentheses around it. So first I have to tell you what is P. I only have two rules. Let's say S derives S derives 0 S1 and it derives 0, 1. So it's actually two productions. You can derive 0 S1 and you can derive 0, 1. Right? So these are my production rules. That's it. So now I'm going to derive some things. So I have not explained what it means to derive something from the grammar, but you kind of know already. So you start with S, and I use my first rule, and I derive 1, 0, 1 S1. What I can do now is I'm going to use the rule here again, and I'm going to derive 0, 0 S1, 1. Right? No, S is always just one S. Here I use the rule that S derives 0 S1 and I substituted it here. So I'm explaining. Let's call this P1. Let's call this P2. I used P1 here. I used P1 again, but inside somehow. And the fact that I'm allowed to do this is written right. It's written out right here. That's why I didn't give you a definition. I'll give you an example. But this means that if you have, I will say that A directly derives B in grammar G, and I will write it this way. If when A is equal to X UV and B is equal to X VU, U derives V. So exactly what this says, that in the middle you can substitute. If U derives V, instead of U, you can substitute with V. This is what I did here basically. Because S derives 0 S1 and I substituted inside. This is what it means to extend production to strings. And instead of giving you this dry definition, let's look at the example. But I can continue this extend production to strings thing again, use maybe P1 again, and I can get 0, 0, 0, S1, 1, 1. And now let's use P2. P2 means I can, instead of S here, I can substitute just 0, 1 without S, and I will get 0, 0, 0, 0, 1, 1, 1, 1. Okay? And the derivation in my grammar is exactly this string, this long sequence here, where I apply my rules again and I end up with terminals. But okay, let's see if we actually do this definition. But let me ask you, so you get this example what I did here, right? So let me give you a definition. A derivation is a sequence of words, W1 to Wn, where each word is a string of terminals and non-terminals, and each next one is the use of the rules on the previous one, and rules meaning you can also substitute inside somehow, the extended production rules. Not only the rules that were written, for example, when I went from here to here, this rule was not written here. However, I was able to use the rule inside, so I'm also allowing that. So this is what G says here, that if I'm going to from WI to WI plus 1 with the rule maybe using inside, I will write that this is the derivation. And the language generated by a grammar is all strings of terminals that are derived from the start symbol. So if I start with my start symbol and I do this derivation rules inside or whatever, I apply my derivation rules and I end up with terminals only, see, terminals, string in terminals, and I start with my start symbol, I will say that this is the language that my grammar creates or my grammar generates. So this was the main distinction between terminals and non-terminals. Non-terminals, the big letters, are the ones that I use in the middle somehow. They give me rules. However, terminals are actually what create strings that I want to generate. So in this case, can you tell me what language will this grammar generate? With n being what? Natural numbers or also 0? Yeah, so natural numbers without. So this is exactly something that we just proved is not regular. This grammar exactly generates things with very simple rules. Rule 1 and rule 2, you can program it on your computer to generate strings like this by just programming these two rules here, and you will generate this language. But somehow we proved that you cannot never construct a DFA that accepts this. Okay, so this is our grammar, and here is the same example, but instead of 0 and 1, we have A and B, but it's the same. Right? Here is our definition of a grammar again, and now I give you all the Chomsky hierarchy. So this is the very important definition here. So I will call. So this is all the languages that grammars create. So, well, this is actually a definition on grammars rather than languages that they generate, but it's the same thing, but so I will say that my grammar is type 0, so I will call it 0, if there is no restrictions whatsoever. That means I'm just given NTPS, N is finite, T is finite, P is something like this. The only restriction really there is that the left-hand side cannot be empty because it makes somehow no sense. So you can derive something from nothing, so you don't want to do this. So only restriction is that, and then you have productions, and if you say nothing else, you will say that your grammar is type 0. Okay, well, when do you say that your grammar is type 1? They also call it context-sensitive grammar. Well, not language, but grammar. Type 1 grammar is a so-called CSG, context-sensitive grammar. If right-hand side of so your grammar has production rules like this, right? U derives V, blah, blah, blah. So if the right-hand side is not shorter than the left-hand side, so you can see this is the requirement. If in all of your productions, the right-hand side is bigger than or equal to the left-hand side, so you're deriving bigger and bigger strings, then you will say that it's context-sensitive. Of course, you can see that this is somewhere here. By the way, you do not know if they're not equal. You do not know if there's something here or not. Maybe, okay, you give me a context-sensitive grammar, that means the productions have longer right sides than the left side, but maybe you give me actually a type 0 grammar with no restriction. I can change the grammar so that it is an equivalent grammar, meaning it generates the same language, but it's context sensitive. So you do not know that this inclusion happens, but let's draw it anyways. ყველა production-ი, რაც წერია გულისხმობ, იმ production-ი ხო ორი string-ია. მარცხენა string-ი უფრო მოკლეა ან იგივე რაც მარჯვენა. So that is context sensitive. Now context-free grammar is even more restrictive, so it will sit here somehow. Type 2 or context-free grammar, which we are aware of, that means that every production rule you have, the left-hand side is just single non-terminal. You cannot have strings anymore. So you have things like this. B derives something, or X derives something. You cannot have strings on the left side anymore. It's just a single non-terminal, and the right side cannot be empty. This is what this says. Because if the left side, if this guy is just a single terminal, then it's always shorter whatever is on the right side if the right side is not empty. So for context-free grammars, you require that the left side is just one letter and the right side is just some string which is not empty. Of course, everything that is context-free grammar is also context-sensitive, because context-sensitive just requires, it has the same requirement as here plus something. And then you have type 3, which is called regular grammar, which just adds one more restriction. Again, it has the same restriction as here, and it adds that every production is like this. So every production is like single letter, let's say A, and then something like this, or something like this. So there's only two types of productions you can use. Single letter derives small letter and a big letter, or single letter derives small letter. That's all. Okay, you can do this. So you can have things like this. You mean this, right? Yes. You can have that A derives AB and A derives A also. So you can use either of your rules. So you have two rules like this, maybe, okay? So this is called regular grammars. And of course you get the... So the idea here is that regular grammars are exactly the ones that generate regular languages. So, and we already know, so let's say you trust me that even though these do not look like DFAs or do not look like stars and concatenations or whatever, how we describe regular languages, let's say you trust me that these grammars exactly generate regular languages. We know that there is something here already. Well, maybe it's not here. It's outside of 3, namely this guy. By the way, maybe this just comes here. Yeah. Let's look at our example again here. How can I... So just look at this example here. Can you say whether this is oh yeah, it just says. It says that it's... Clearly this grammar is context-free. Because what was the requirement of context-free, right? The requirement for context-free, you cannot see it anymore. Oh, here. The requirement of context-free is that the left side is just single letter and the right side is longer, not empty. Clearly this works because you only have two production rules like this here, and clearly left side is single letter and the right side is not empty. So clearly this grammar is context-free. So what we just proved then is that if you trust me that type 3 is the same as regular and type 2 is context-free, we just proved that there is a guy here. There is a guy here, namely this thing, AN, BN, this language that is not regular but is context-free. And then you can prove that there is something here, and there's a whole different world to prove that something is here. This is what Alan Turing did, that there is something here. And we will see when we continue that anything that can be computed, this is Church's thesis, by the way, but somehow this is very, it's a thesis that says that you should trust, probably. Otherwise, if you don't trust it, then everything we're doing in computer science and mathematics is broken in some sense. But what Chomsky says that everything that can be computed is type 0, basically. Every algorithm that can be written down or anything that can be computed is basically a type 0 thing. So type 0 is everything computable, then type 1 is better guys, so more handleable things, then type 2, and then regular ones are the DFAs, basically the easiest questions to answer.
Something here she has
Anu. What I mean is that a language is, so yeah, I shouldn't have said, I went, so type 0 is a grammar. So type 0 is a definition for a grammar. The grammar is type 0 if it has no restrictions. It's just basically this. This is type 0. There's nothing is restricted. If you can write down a grammar, then this is type 0. I will also call a language type 0 if it's generated by type 0 grammar. Let's try to record why this is a problem. Let's imagine the thing that you learned in school or whatever, in university, real numbers, right? Let's go to, or maybe even, let's go to real numbers because it's something we all know. So real numbers. So they tell you that real numbers is all possible combinations of, so it's things like 0, 1, pi, square root of 2, and blah, 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 blah. But I'm telling you that all the numbers that you know of, or even all the numbers that you can think of, or all the numbers that humankind can ever write down any procedure to calculate, they are just like size 0 in real numbers. So what I mean by this is that, let's say your pi, right? Blah, 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 blah. So this is your pi. You know that this guy is irrational, right? It goes on to infinity and it kind of never repeats the pattern. However, you can write down an algorithm, basically, that computes any digit of pi, given enough time and enough space. So there exists an algorithm that you can give, I don't know, 10 to the power 16, whatever, an input, and it will give you the 10 to the power 16th digit of pi. Maybe it's not feasible in real world because it takes too much time, but the algorithm exists. That means there exists what is an algorithm, right? There exists a finite string. It's a finite string that completely describes pi. In a sense that it describes in a way that it contains all the information of pi, in the sense that it can compute any digit of pi. Same thing with square root of 2, and so on. So there exists a finite string that describes it. However, what I'm telling you that the most numbers here, in a precise sense of most, are not describable by an algorithm. They're so random in a sense that, let's say the number like 0, 1, I can never write it down because it's not describable. Right? So most numbers are so random in a sense that there does not exist a finite string that will describe them. Those are not intuitively type 0. So type 0 is things that are describable by finite strings. That means we will also call it computable, whatever this means. So type 0 is something that, so what was grammar, right? Grammar was just some non-terminal, terminal, blah, 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 and then start symbol. And the most important part here was a production rule. So the production rules are your algorithm, how you create strings somehow. And type 0 says that there exists an algorithm for this language to create strings. If you talk about real numbers as mathematicians define, there does not exist a finite algorithm which will describe you all real numbers. There's just far too many of them. However, those real numbers that are somehow for which we will ever use, any real number that humankind will ever use, will have an algorithm that comes with it to compute it. Otherwise, it makes basically no sense. They exist in some world there, and you can never write them down. You can never write down the finite string that describes them. So there's like undescribable, but most of real numbers are there, are like that. So I talk too much philosophy. Okay, so enough with the philosophy here. So we go back to this place. So we still have some time. So you already know context-free grammars, as I believe, and so you are supposed to know what. Now, context-free grammars have derivation trees. Who has seen derivation trees? So everybody has seen derivation trees. Almost everybody. Very nice. So let me just remind you what derivation trees only work for context-free grammars. They do not work for sensitive grammars and so on. So let's just look at it one. Context-free grammar, CFG, is something that you have one letter and a non-empty string on the right. So let's look at what a derivation tree is. So derivation trees, I took it from your textbook. By the way, we have basically two textbooks we're following. Hopcroft and Ullmann, it's in your syllabus. It's like a Bible for this thing. And Michael Zipser, which is an MIT textbook. We'll follow these two. So this is a derivation tree definition. I took it from Hopcroft and Ullmann, and I just changed it to your notation. So let's say we are given a grammar NTPS, and let's say it's context-free grammar. So all my P's have one letter on the left and non-empty on the right. Now let's say I have a tree. A tree is a derivation tree for a grammar if these four things hold. First, every node in my tree has a label, which is either terminal or non-terminal. The label at the root is a start symbol. This is number two. Now, if node in my tree has at least one descendant other than itself somehow, so it has sons, and let's say my node has label A, then A must be a non-terminal. This means that terminals do not have descendants. You cannot derive anything from a terminal. Only non-terminals have descendants. This is number three. And now, number four, the most important one, is that if nodes n1 to nk are direct descendants of node n, so you have n and then k descendants, in order from left to right, with labels a1 to ak, then you have to have a production a produces a1 to ak. So you build your tree from productions, basically that's what it's saying. And let's look at an example. So example is this thing here. So let's look at an example here. This again from Hopcroft and Ullmann. Let's say this is our grammar. The grammar has two non-terminals, S and A. It has two terminals, A and B, so it just derives strings consisting of A's and B's, and production rules and start symbol. And I have 1, 2, 3, 4, 5 production rules. S, A, S, A, S, B, A, S, 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 A, B, A, whatever. Let's actually copy this to OneNote and look at it more carefully. Paste it. Why don't you paste it? Picture here. So this is our thing that we're looking at now, and this is a derivation tree. Can you tell me? Well, it says here, but this derives AA, BB, AA. But can you give me a derivation in a written form? So I start with S. What is the next thing I'm using? Next rule that I'm using according to this derivation tree. Yeah, AAS. So it's basically this guy. What am I doing next? I'm using a derivation. So S has to be big here. So what is the next thing that I'm using? So I'm using something in the middle. So maybe I write A, S, B, S, B, A, and then S just carries over, right? So I'm using this guy here. And then here I'm also using this thing. You can see I can write A, S, B, A like this. And then it continues. And you arrive at A, B, B, A. So somehow I see that you all are aware of this, right? I'm just claiming there's a confusion usually that derivation tree just derives a word. It's not a grammar. Derivation tree is a derivation of a single word in the language that grammar derives. So you cannot construct a grammar from a tree. Same grammar gives you millions of trees, maybe. But somehow you see how this works. By the way, how would I know that this thing is derived? So this is A, right? A, B, B, A, right? But how did I know to read it this way? How did I know the sequence how to read? For example, how do I know that this guy, let's say, is to the left of this guy? Yeah, what you do is you look at you look at any two leaves, let's say, I don't know, let's say this guy and this guy. How do I know that this leaf comes first? I go up to find their common parent. This is their common parent, like here. And then one is always to the left side of the common parent and the other one is to the right side. And the one that is on the left side comes first. So you just go up, find a common ancestor, and then all the leaves are ordered from left to right. This is how I write these things. They're ordered from left to right, so you get the point. So whoever is on the left comes first. Esa. I just used the production, this guy in the middle. Yeah, it does. Huh? You were asking why did I use this and not this first? I saw it here exactly. SBA. So I had something like this. A derives SBA. This was a subtree here, sitting at the blue part. So this was exactly this. And this was, by the way, this is the requirement. This is requirement number 4, that if I have a node n and descendant, this has to be a production rule. This is what number 4 says. That if you have a node n and its descendants n1, nk, and they are labeled like this, then it has to be a production. I only can expand my tree following the productions. And by the way, now, this lemma 1 that goes here, you can see, let me read what lemma 1 said, and this is an exercise on your worksheet, and this is one of the harder exercises, and I just don't think anybody will be able to do it completely, not because it's hard, it's more because it's complex. And what you can do is you can go to Hopcroft and Ullmann, this is proven there, and if you read it and understand it, that's also a feat. So understanding this is also a very good thing to do. But this is an exercise, you can try to prove it. The exercise says that you start with a context-free grammar G, and you have a non-terminal L, N, and let's say you have a word. So W is NT plus. Then there is a derivation tree for G with root B and border word W. Border word means you read it on the leaves. If and only if B derives W. So what this proves is basically that derivation trees exist if and only if you can derive it in the grammar, and vice versa. If you can derive it in the grammar, you can construct a tree. If you have a tree, you can put it in the grammar. So context-free grammars and derivation trees and the string of derivations are the same. I mean, it's somehow obvious in a sense, but in order to prove it, as I said, it's not hard, it's complex. So you have to keep track of many things and do an induction on the length of it to actually prove it mathematically. So basically the definition of LG with derivation trees and the derivations give the same result. So either you define it with a grammar or by derivations or by derivation trees, that will give to you the same thing. Okay, so we still have some time, and we might as well gain ground because we were behind, and I'm suspecting this will happen again. So now what we're saying is this. So let's look at the definition of grammars again, and let me ask you a question. What I'm planning to do is what we did with regular grammars. What we did is regular languages. What we did is we defined a regular language, and then we defined a machine that is the same as basically a regular language. This was a DFA. What I want to do is I construct a machine for context-free grammars. This would be, spoiler alert, a push-down automaton. So there's a push-down automaton. This is a machine that also has, in some sense, an infinite memory. But anyway, so then this will be a machine exactly that accepts context-free grammars. Then there is a machine for context-sensitive grammar. We will also do this in the end. But first, and then there is a machine that accepts type 0 languages. This is a Turing machine. So type 0 languages is basically, as I explained in my intuitive explanation, is anything that can be algorithmically described, and it's basically type 0 things are accepted by Turing machine. And the fact that this is anything that can be algorithmically described is the church thesis. This is a belief that we all believe in, because we do not have we can discuss this later. So we do not have a specific definition of computation, but anyways. So Turing machines will be type 0. Linearly bound, so the specific types of Turing machines will be type 1, so not all Turing machines, but some type of Turing machines will accept type 1. Then type 2 will be push-down automata, and type 3 is DFA, basically. But now I'm asking you a question. Let's say this is my plan, this is what I want to do. Now I'm asking, does type 3 grammar allow you to derive a language that contains an empty string? Or maybe does type 1, so there is 0, does type 1 grammar allow you to create a language, that means derive a language that has empty string in it? Exactly. So I just written it that the right, even let's look at type 2. It's written out like this way. So it's true for type 1 also in type 2 that if I have a context-free grammar, the left-hand side is just single letter and right-hand side is longer than the single letter. So it cannot be empty. So basically you can never derive an empty string. The same is true for regular grammars. So what is a regular grammar? Its left-hand side is a single letter and right-hand side is single letter follows AB or single letter follows A. It does not include something epsilon. So you can never derive something that is empty. However, let me give you a DFA. Let's say again my alphabet is just B, and this is my DFA. What language does, so let's call this guy M. What language does this DFA accept? So it's basically B star, right? So it's zeros, ones, all possible strings, and also epsilon. So epsilon is here. So now I'm claiming that I gave you a definition here. There was this definition that, and I promised that regular grammar is exactly the ones that DFAs accept, but I just gave you a DFA that accepts empty, but this regular grammar will never accept an empty string. So it's somehow banned. And any machine I construct, so this, by the way, this is the start state here, I forgot. So any, let's say DFA I construct, if the start state is also the accepting state as here, then it will accept an empty string. Do you agree? If my start state is also an accepting state, it will always, so epsilon will be in LM, if start state is accepting. This will also be true in push-down automata, which I have not defined, or blah, blah, any automata I construct. If the start state is also accepting, so if the state you start with is also accepting, then you will have epsilon in your language. What I want to do now is I want to allow my grammars to accept epsilon. I want to change this definition a little bit, so I'm also allowed to generate empty strings. How I define it here, like for example here, only type 0 allows. Type 0 has no restriction, so you can have things like this. And you will then generate, maybe start state generates epsilon, and then you have epsilon. However, number 2, or type 1 already says that the right-hand side has to be longer than the left-hand side or equal, and the left-hand side cannot be empty. So it already bans epsilon. So what I want to do is I want to change my grammar in a way that it generates epsilon and nothing else. This is what is written here, and I'm asking you a question. How do I do this? How do I do, let's look at our notes again. Like maybe here. Let me erase this. So let's say this is my grammar. So not this particular derivation tree, but this grammar here. This is my grammar. This grammar does not, this is a context-free grammar as I defined it. This does not generate, it never generates an empty string. How can I want to, so this generates some language, I don't know what language this is, whatever, LG is, I know for sure that A, B, A is here, because it has a derivation, but this language does not include epsilon, because there's no production that can create epsilon. Now I'm asking you, can you add a production here that generates epsilon? I just want this. I want to create a language. Just add single thing epsilon and nothing else. I want to add a production here that generates an epsilon and nothing else. Yeah, that's actually a good idea. Maybe add this, you're saying. Epsilon is basically nothing, so you cannot make it. So epsilon is an empty string. It's not a letter somehow. But this is actually a good idea to do this. So S derives epsilon. But now look what I did. I had this derivation here, right? Let's look at this derivation. This derivation said A derives SBA. But now I can have S epsilon. So I can use this here, and this derives BA. Is that right? So I have something else going on now. Now so this is actually okay because I already had this here. But let's use it at a different place. I had this string A derives SS. So this means I can use epsilon twice, and this also derives epsilon now. So A derives epsilon. So now this here, the first rule, S derives AS, is now A derives epsilon. So this derives AS. S derives S, so this derives A. So I'm doing some other things now because the fact that I introduced this new rule here broke old rules. In a sense, it added much more things than just epsilon. So it added that I can derive A. I don't know if I could derive A. Maybe yes, here it was. But you know what I mean, right? So when you added this rule, you're also adding some other rules that you didn't intend to add. So my question is, what do we do now? If I add this, what was the problem? What created new rules? Exactly. So this is new start state. So basically what you're supposed to do. So the problems that were created here is that if you have S on the right side, namely here, here, and here, then you're adding a new rule that you can erase that S, that you do not want to add new rules. So what you want to do is you want that you do not have start states on the right side, basically. So what you will do is whatever was suggested, you add a new start state, S prime will be your start state, and then you add this rule, and what else should you add? Yeah, S prime gives you S, and that's it. So S prime now is your new start state, so this will become S prime. S prime gives you S, so all these rules can be used again because of this. And then you have just one rule here, and nothing is broken because S prime never appears on the right side. Context-free აღარ იქნება ესე რო ვქნა? Yeah, that's actually a good question. So let's look at the rules again. So you will answer your question yourself. So where was this? Yeah, here. So the rules say that the right-hand side is bigger or equal to whatever is written on the left. That will not be violated. In the epsilon, so what I will do is I'm going to redefine context-free grammars, let's say, such that this holds, plus there is just one more rule like this. And I will give an exception for this one rule. This rule, and for everything else, this holds. And this is what is done here, exactly what you said. And then exactly this is what you said, and this is what you said. Okay, let's stop for today, and then we continue tomorrow.